Let's study stationary wave formation in a string clamped at one end. Say we are given with a string which is clamped at one end at a wall, and say the open end is made to oscillate. Then in this situation a wave starts propagating from the clamped end. It will be reflected, and the propagating wave and the reflected wave may superpose and produce stationary waves here. But the condition of a stationary wave formation here will be a node must be produced at the clamped point as it cannot oscillate, and the point which is being oscillated must act as an antinode as it can never be at rest. Now in this situation, if this is acting as an antinode and this as a node, the maximum wavelength which can be sustained in the string will be such that the length of a string is equals to lambda by 4, such that these 2 points will act as closest node and antinode. If the length of a string will act as lambda by 4, we can find out the oscillation frequency of a string as n naught is V by lambda, which can be written as here lambda will be 4L. So it is V by 4L, it is 1 by 4L root of T by mu. This is the frequency we can call fundamental frequency, or this is the minimum frequency at which the stationary wave can be obtained in such a manner. Now if we talk about the next possible frequency at which the string can oscillate in stationary waves, that will be the situation again when the clamped end will act as a node and oscillating end will act as antinode. So we can introduce another node in between, and the situation would be like this. In this situation again a stationary wave can be obtained. One loop is introduced here. So in this situation the length of a string can be written as 3 lambda by 4, because one complete loop and one half loop is there in the length L of a string. So here the wavelength can be written as 4L by 3. If we find out the oscillation frequency, it is V by lambda, which is V by lambda is 4L by 3. So it can be written as 3 times the fundamental frequency. So it can be written as third harmonic. And here we can see in case of clamped string oscillation, second harmonic is not available. So this is the first overtone of clamped string oscillation, which is clamped at one end, at which after fundamental frequency stationary wave is obtained. So there exists no frequency between n0 and 3n0 at which stationary wave can be established. Similarly, I hope all of you can judge here which will be the second overtone or the next possible frequency at which stationary wave can be obtained. Yes, here we'll introduce one more loop. So you can see the string will oscillate in this manner. The open end will be acting as an antinode and closed end is again a node. And here the length can be written as 5 lambda by 4. And the wavelength is 4L by 5. So correspondingly the frequency is V by lambda, which can be written as 5V by 4L, or it is 5 times the fundamental frequency. It can be written as N5, this can be written as N3, this fifth harmonic. So we can say in case of clamped string oscillations, resonance can be established only at odd harmonic frequencies of the fundamental. If external source which is brought and the string is made to oscillate with the frequency which is even multiple of fundamental, then also the energy will damp out and no resonance will occur. So we can say in case of strings which are clamped only at one end, only odd harmonic frequencies are available for formation of stationary waves.